Where did everything we are made of come from? This question has puzzled humanity since we first looked up at the stars and wondered about our place in the cosmos. The answer takes us on a journey through time and space, from the very first moments of existence to the complex chemistry that flows through our veins today. To understand where the elements came from, we must travel back to the beginning of everything we know. 13.8 billion years ago, there was no space, no time, no matter as we understand it. There was only an infinitesimally small point of unimaginable energy and density. This singularity contained everything that would ever exist, compressed into a space smaller than the smallest particle we can imagine. Then, in an instant that defies all our everyday understanding of reality, this point began to expand. Not into empty space, for there was no space to expand into. Rather, space itself came into being, stretching and growing at a rate that makes light seem to crawl. This moment, this cosmic dawn, is what we call the Big Bang. But it was not an explosion in the way we might picture an explosion. There was no sound, for sound needs air to travel through, and there was no air. There was no brilliant flash of light, for light itself had not yet formed. Instead, there was pure energy transforming into the fundamental building blocks of everything. In the first fraction of a second after this beginning, the universe was hotter than anything we can truly comprehend. The temperature was trillions upon trillions of degrees, far beyond what exists in the cores of the most massive stars. At these temperatures, even the basic particles of matter could not hold together. Protons and neutrons, the building blocks of atomic nuclei, existed only as a soup of even more fundamental particles called quarks and gluons. As the universe expanded, it cooled. Like steam condensing into water droplets as it cools, the energy of the early universe began to condense into the first particles of matter. Within the first few minutes, the temperature had dropped enough for protons and neutrons to form from the quark soup. These protons were nothing more than hydrogen nuclei, the simplest possible atomic core consisting of just a single proton. But the story of element creation was only just beginning. In those crucial first few minutes, while the universe was still incredibly hot and dense, something remarkable happened. Some of the protons and neutrons began to stick together, forming the nuclei of the second lightest element, helium. This process, called Big Bang nucleosynthesis, was like a cosmic cooking pot, where the ingredients of the early universe were being stirred together under the most extreme conditions imaginable. The recipe for this primordial cooking was precise and unforgiving. For every 100 hydrogen nuclei that formed, about 25 helium nuclei came together. A tiny fraction of lithium, the third lightest element, also emerged from this cosmic kitchen. But then, as quickly as it had begun, this first epoch of element creation came to an end. The universe had expanded and cooled too much for nuclear fusion to continue. The cosmic cooking pot had gone cold. For hundreds of millions of years, the universe was a relatively simple place. It contained mostly hydrogen and helium gas, along with mysterious dark matter that we still don't fully understand today. There were no stars, no planets, no complex chemistry. The universe was dark, filled only with these primordial gases slowly swirling and clumping together under the influence of gravity. But gravity is patient and persistent. Over vast stretches of time, the hydrogen and helium began to collect in ever larger clouds. These clouds grew denser and denser as more gas fell into them, drawn by their own gravitational pull. As the gas compressed, it began to heat up, just as air heats up when you compress it in a bicycle pump. Deep in the centers of the largest clouds, the temperature and pressure began to climb toward levels not seen since those first moments after the Big Bang. Eventually, in the heart of these collapsing gas clouds, something magnificent happened. The temperature reached 10 million degrees, hot enough for hydrogen nuclei to overcome their natural repulsion and slam together with such force that they fused into helium. This nuclear fusion released tremendous amounts of energy, enough to make the entire cloud begin to glow. The first stars had been born. These ancient stars, formed from the pristine hydrogen and helium of the early universe, were unlike any stars we see today. They were massive beyond imagination, some containing hundreds of times more material than our Sun. They burned with fierce intensity, consuming their nuclear fuel at prodigious rates. Their surfaces blazed with temperatures of 50,000 degrees or more, making them shine with a brilliant blue-white light that could be seen across vast distances. Inside these stellar giants, the process of element creation continued where the Big Bang had left off. In their cores, where temperatures reached hundreds of millions of degrees, hydrogen fused into helium in a carefully choreographed nuclear dance. 4 hydrogen nuclei would come together through a series of steps to create one helium nucleus. In the process, they released the energy that kept the star shining and prevented it from collapsing under its own immense weight. But helium itself could become fuel for even more exotic nuclear reactions. When the core temperature climbed to 100 million degrees, helium nuclei began to fuse together. 3 helium nuclei, each containing 2 protons and 2 neutrons, could combine to form carbon, an element with 6 protons in its nucleus. This process, discovered by the astronomer Fred Hoyle, seemed almost impossibly unlikely. The nuclear physics involved required an extraordinary cosmic coincidence, as if the universe had been fine-tuned to allow carbon, the foundation of all organic chemistry, to exist. With carbon established in the stellar cores, the story of element creation accelerated. Carbon nuclei could capture additional helium nuclei to form oxygen, with 8 protons. Oxygen could capture more helium to become neon, with 10 protons. Each step required higher and higher temperatures, and each step released energy that kept the star burning ever more brightly. As these first massive stars aged, their cores became like cosmic onions, with different nuclear reactions occurring in concentric shells. The outermost shell continued to fuse hydrogen into helium. Deeper in, helium fused into carbon and oxygen. In even deeper shells, carbon fused with itself to create heavier elements like magnesium, sodium, and aluminum. Oxygen nuclei collided and fused to produce silicon, phosphorus, and sulfur. The nuclear reactions in these stellar cores proceeded with increasing urgency as the stars aged. Each successive stage of fusion happened more quickly than the last. The hydrogen burning phase might last for millions of years. Helium burning lasted for thousands of years. Carbon burning lasted for hundreds of years. Oxygen burning lasted for months. And finally, silicon burning, the last stage of nuclear fusion that could power a star, lasted for only days. During silicon burning, the star's core became a nuclear foundry operating at temperatures of several billion degrees. Silicon nuclei, each containing 14 protons, were broken apart and rebuilt in countless combinations, creating a whole range of elements: titanium, chromium, manganese, iron, cobalt, and dash. Nickel. The element iron, with 26 protons in its nucleus, marked a crucial threshold. Iron represents the most stable configuration of protons and neutrons possible. Elements lighter than iron release energy when they fuse together, but elements heavier than iron actually absorb energy when they are created. This meant that once a star's core filled with iron, its nuclear fires began to die. Iron cannot fuse to create heavier elements and still power the star. The energy source that had supported the star against the crushing force of its own gravity for millions of years was exhausted. The stellar core, now made of iron and weighing more than our entire sun, began to collapse. What happened next was one of the most violent and spectacular events in the universe. The iron core collapsed in less than a second, shrinking from the size of the Earth to a ball only 20 kilometers across. The matter became so dense that atomic nuclei were crushed together, forming a solid mass of neutrons packed tighter than anything else in the universe except black holes. A teaspoon of this neutron matter would weigh as much as a mountain. The collapse happened so fast that the outer layers of the star had no time to react. They continued falling inward, accelerated by gravity, until they slammed into the newly formed neutron core at speeds of 30,000 kilometers per second. The collision created a shock wave that raced back out through the star, carrying with it more energy than our sun will produce in its entire 10 billion year lifetime. This was a supernova, the explosive death of a massive star. For weeks, a single supernova could outshine an entire galaxy of 100 billion stars. The explosion was so violent that it could be seen from billions of light years away, a cosmic lighthouse announcing the death of a stellar giant. But this destruction was also creation on a cosmic scale. The tremendous energies unleashed in the supernova explosion finally provided the conditions needed to forge elements heavier than iron. For the first time since the Big Bang, there was enough energy available to force protons and neutrons together into nuclei that didn't want to form. In the incredibly hot, dense environment of the supernova shockwave, rapid cascades of nuclear reactions built up the entire periodic table of elements. Cobalt and nickel formed first, elements just slightly heavier than iron. Then came copper and zinc, followed by gallium, germanium, and arsenic. The process continued through silver and tin, reaching all the way up to gold, mercury, and lead. Even the heaviest naturally occurring elements like thorium and uranium were forged in these stellar explosions. The supernova was not just creating these elements but scattering them across space. The shock wave blasted the star's outer layers into the surrounding void at thousands of kilometers per second, carrying with it all the elements that had been created during the star's lifetime and death. Carbon, oxygen, silicon, iron, gold, and hundreds of other varieties of atomic nuclei began their journey through interstellar space. These ancient supernovae were cosmic gardeners, seeding space with the chemical diversity needed for complex structures to form. The expanding shells of gas and dust they created, called supernova remnants, traveled for thousands of years, mixing their newly minted elements with the primordial hydrogen and helium that still filled most of Teal. Space. Over time, these enriched gas clouds began to condense once again under their own gravity. But now the collapse was different. The new elements, though still a small fraction of the total mass, changed everything. Elements like carbon and oxygen could form molecules even in the cold of interstellar space. These molecules radiated away energy much more efficiently than simple hydrogen and helium, allowing the gas clouds to cool and collapse more readily. The second generation of stars that formed from this enriched material were smaller and longer lived than their massive predecessors. They burned their nuclear fuel more conservatively, allowing them to shine steadily for billions of years rather than millions. Our Sun is one of these second-generation stars, born from gas that had been enriched by countless previous generations of stellar death and rebirth. But the story of element creation was far from over. While smaller stars like our Sun could produce elements up to carbon and oxygen in their cores, they lacked the mass to create the heaviest elements through supernova explosions. For these most exotic elements, the universe required even more extreme conditions. Those conditions exist in the collision of neutron stars, the ultradense remnants left behind by some supernova explosions. Neutron stars are among the most extreme objects in the universe. They contain more mass than our Sun, yet they are compressed into a sphere only 20 kilometers across. Their surfaces are so hot they glow with X-rays, and their magnetic fields are trillions of times stronger than Earth's. A sugar cube-sized piece of neutron star material would weigh as much as all of humanity combined. When two neutron stars orbit each other, they gradually spiral inward, losing energy by radiating gravitational waves that ripple through the fabric of space-time itself. Eventually, after millions of years of this cosmic dance, the two neutron stars collide in an event so violent it can be detected by gravitational wave observatories on Earth from billions of light-years away. The collision lasts only milliseconds, but in that brief time, conditions become even more extreme than those inside a supernova explosion. The neutron-rich matter is torn apart and reformed under pressures and temperatures that push the boundaries of physics. Rapid neutron capture processes, happening faster than the newly formed nuclei can decay, build up elements far heavier than anything created in stellar cores or supernova explosions. It is in these neutron star mergers that the universe's rarest and most precious elements are born. The gold in our jewelry, the platinum in our electronics, the uranium that powers nuclear reactors, the iodine essential for our thyroid glands, all of these elements were likely forged in the violent collision of neutron stars somewhere in the cosmic past. The collision also creates a kilonova, an explosion that glows with the light of a billion suns for weeks or months. This light comes primarily from the radioactive decay of the newly created heavy elements, including gold and platinum. The explosion launches these precious elements into space at tremendous velocities, where they mix with the interstellar medium and eventually become incorporated into new stars and planetary systems. Through this cosmic recycling process, the universe has steadily increased its chemical complexity over billions of years. Each generation of stars has added new elements to the mix, creating an ever richer palette of atomic building blocks. What started as a universe of only hydrogen and helium has become a cosmos containing all 94 naturally occurring elements, from the lightest hydrogen to the heaviest uranium. This process continues today. In observatories around the world, astronomers detect the light from distant supernova and kilonovae, witnessing element creation happening in real time across the cosmos. The Hubble Space Telescope captures images of supernova remnants thousands of years after the initial explosion, showing how the elements are still spreading through space, carried by shock waves that light up the surrounding gibbs. Gas in brilliant colors. Each color tells a story of nuclear creation. The red glow comes from hydrogen, still the most abundant element in the universe. Blue and green light comes from oxygen, forged in the cores of massive stars. Yellow light reveals sodium, while purple indicates sulfur. These cosmic fireworks displays are actually chemical fingerprints, allowing astronomers to catalogue the elements being dispersed through space. Closer to home, we can see the evidence of this stellar alchemy all around us. The oxygen we breathe was created in the core of a massive star that exploded long before our solar system formed. The carbon in our bodies, the foundation of all organic chemistry, was manufactured through the triple alpha process in stellar cores. The calcium in our bones and teeth was synthesized during explosive stellar nucleosynthesis. Even the iron in our blood carries an ancient cosmic heritage. Every iron atom in our bodies was forged in the final moments of a dying star, created during the last desperate seconds before the stellar core collapsed. When we hold an iron nail or look at the red color of rust, we are seeing matter that was born in conditions of unimaginable violence and heat, billions of years ago and trillions of miles away. The rarer elements in our bodies tell even more exotic stories. The iodine concentrated in our thyroid glands was likely created during the collision of neutron stars, in an event so energetic it sent ripples through spacetime itself. The tiny amounts of gold in our bodies, present in every cell though in concentrations measured in parts per billion, are stellar artifacts from some of the most extreme events in cosmic history. This connection between stellar nucleosynthesis and biological chemistry goes far deeper than mere curiosity. Life itself depends critically on the cosmic production of heavy elements. Carbon forms the backbone of organic molecules because of its unique ability to form 4 chemical bonds, allowing it to create the complex chains and rings that make proteins, DNA, and other biomolecules possible. This property exists only because of the precise nuclear physics that governs carbon's formation in stellar cores. Oxygen is essential for the energetic metabolism that powers complex life, but it could not exist without the nuclear reactions in massive stars. Iron enables the hemoglobin in our blood to carry oxygen throughout our bodies, but every iron atom required the extreme conditions of stellar cores to come into being. Phosphorus forms the backbone of DNA and the energy-storing molecules in our cells, but it too was created through stellar nucleosynthesis. Even the trace elements that our bodies need in tiny amounts often have remarkable cosmic origins. Zinc, essential for immune function and wound healing, was created during supernova explosions. Copper, needed for connective tissue and nerve function, was forged in the same stellar foundries. Selenium, a powerful antioxidant, owes its existence to the nuclear processes in dying stars. The water we drink carries its own cosmic history. While the hydrogen atoms in water are primordial, dating back to the first few minutes after the Big Bang, the oxygen atoms were created much later in stellar cores. Every molecule of water therefore represents a marriage between the very oldest and much younger atoms in the universe, a chemical union that spans nearly the entire history of cosmic time. The story becomes even more remarkable when we consider that these elements had to travel immense distances through space and time to eventually become part of living beings. The supernova that created the iron in your blood might have exploded 5 billion years ago in a distant part of our galaxy. The shockwave from that explosion launched iron atoms on a journey through the interstellar medium that lasted millions of years. Those iron atoms drifted through space, sometimes alone, sometimes incorporated into dust grains, occasionally caught up in the formation of new stars that later died and dispersed their contents once again. Eventually, about 4.5 billion years ago, they became part of the rotating disk of gas and dust that was collapsing to form our solar system. In that swirling disk, the heavier elements began to stick together, forming the first solid particles in our nascent solar system. Iron atoms bonded with oxygen to form iron oxide dust grains. Silicon combined with oxygen to create tiny crystals of silicate minerals. Carbon atoms link together in complex organic molecules. These microscopic solid particles gradually accumulated into larger and larger clumps, eventually forming asteroids, comets, and planets. Our Earth formed through this process of accretion, growing from a collection of dust grains to a planetary body through billions of collisions with asteroids and comets. Each impact delivered more stellar-manufactured elements to our world. The iron that sank to form Earth's core, the silicon and oxygen that make up most of the rocky mantle, the carbon that would eventually become the foundation of life, all of these elements had been created in stars and dispersed through space by cosmic explosions. The early Earth was a molten, chaotic world, bombarded constantly by asteroids and comets. But even in this hostile environment, the stellar elements began to organize themselves into increasingly complex structures. Iron and nickel sank toward the center, forming a metallic core that generates Earth's protective magnetic field. Lighter silicate minerals floated toward the surface, creating a rocky crust. Water delivered by countless icy comets began to accumulate in low-lying areas, forming the first oceans. In those ancient seas, stellar carbon began to participate in ever more complex chemical reactions. Carbon's ability to form long chains and intricate branching structures allowed it to create molecules of unprecedented complexity. These organic molecules could store information, catalyze chemical reactions, and even reproduce themselves. Through processes we still don't fully understand, this stellar carbon organized itself into the first primitive forms of life. Life on Earth is therefore a direct continuation of the cosmic process of increasing complexity that began with the first stars. The same nuclear forces that created carbon in stellar cores also govern the chemical bonds in DNA. The same physical laws that drove supernova explosions also control the metabolism of living cells. We are not separate from the cosmic story of element creation, we are its most recent chapter. Every breath you take cycles stellar oxygen through your lungs. Every beat of your heart pumps stellar iron through your veins. Every thought you think relies on the electrical properties of stellar sodium and potassium. The very neurons firing in your brain as you contemplate these ideas are made of atoms forged in the nuclear furnaces of ancient stars. This realization transforms our understanding of what it means to be human. We are not merely observers of the universe, but active participants in its ongoing story of creation and evolution. The elements that make up our bodies will not remain bound together forever. When we die, those atoms return to the environment, eventually to be incorporated into new living beings or perhaps launched back into space by geological processes. In a very real sense, we are temporary arrangements of stellar matter that have gained the ability to contemplate their own cosmic origins. The carbon atoms in our DNA carry within their nuclear structure the history of the stars that created them. The iron atoms in our blood remember the violent moments of their birth in supernova explosions. We are living libraries of cosmic history, walking repositories of information about the universe's chemical evolution. This perspective also reveals the profound unity underlying all life on Earth. Every living thing, from the smallest bacterium to the largest whale, is made of the same stellar elements arranged in different patterns. The oak tree in your backyard and your pet cat both trace their atomic heritage back to the same cosmic sources. We are all made of star stuff, as the astronomer Carl Sagan famously observed, participants in a grand cosmic recycling program that connects us to the most distant galaxies and the most ancient times. The elements that make up our world are still being created in stars throughout the universe. At this very moment, Massive stars are fusing lighter elements into heavier ones in their cores. Somewhere in a distant galaxy, a supernova may be exploding, forging new gold and platinum that will someday become part of an alien world. Neutron stars are colliding, creating the heaviest elements and launching them into space to begin journeys that may last billions of years. Our own Sun continues this ancient process of element creation, though on a more modest scale. In its core, hydrogen is steadily being converted into helium through nuclear fusion, the same basic process that powered the first stars billions of years ago. Eventually, in about 5 billion years, our Sun will exhaust its hydrogen fuel and begin to fuse helium into heavier elements. It will expand into a red giant star, incorporating elements created in its core into its outer atmosphere. When our Sun finally dies, it will not have the mass to explode as a supernova. Instead, it will gently puff off its outer layers, creating what astronomers call a planetary nebula. This expanding shell of gas will carry the elements created in the Sun's core out into interstellar space, where they will mix with the cosmic medium and eventually become part of new stars and planets. In this way, our Sun will contribute its own small chapter to the ongoing story of cosmic chemical evolution. The carbon and oxygen atoms created in its core may someday become part of new worlds orbiting distant stars. They may even become incorporated into new forms of life that we cannot yet imagine, continuing the ancient cycle of stellar death and rebirth that has been operating since the first stars began to shine. The story of the elements is therefore not just a story about the past, but an ongoing narrative that continues to unfold throughout the universe. Every star that shines, every supernova that explodes, every neutron star collision that ripples space-time is adding new chapters to this cosmic tale. The elements are not static building blocks, but dynamic participants in the universe's continuing evolution. Modern astronomy has revealed that this process of element creation is not uniform throughout the cosmos. Galaxies that formed early in cosmic history are relatively poor in heavy elements, containing mostly hydrogen and helium with only small traces of heavier elements. These ancient galaxies shine with the blue light of massive, short-lived stars that are still in the process of creating and dispersing heavy elements for the first time. In contrast, regions of the universe where star formation has been ongoing for billions of years have built up substantial reserves of heavy elements. Our own galaxy, the Milky Way, falls into this category. After nearly 14 billion years of stellar evolution, our galaxy has accumulated enough heavy elements to form rocky planets like Earth and support the complex chemistry needed for life. Even within our galaxy, there are significant variations in heavy element abundance. Stars in the galactic center, where star formation has been most active, tend to be richer in heavy elements than stars in the outer regions. Stars that formed recently from gas clouds enriched by many previous generations of stellar death contain more heavy elements than ancient stars that formed from more pristine material. These variations in element abundance have profound implications for the possibility of life throughout the universe. Planetary systems forming around metal-poor stars may lack the heavy elements necessary for rocky planet formation. Even if such planets do form, they may lack the chemical diversity needed to support complex biochemistry and life as we know it. This suggests that life may be more common in some parts of the universe than in others. Regions with long histories of active star formation and multiple generations of element-enriching supernovae explosions may be more likely to host habitable worlds. Our location in the Milky Way, in a region with moderate heavy element abundance and a relatively stable environment, may represent something of a cosmic sweet spot for the development of complex life. The search for life elsewhere in the universe therefore depends critically on understanding the cosmic distribution of heavy elements. Astronomers studying distant galaxies and star-forming regions are essentially mapping the chemical evolution of the cosmos, identifying regions where the stellar alchemy has progressed far enough to make biological chemistry possible. Recent observations with advanced telescopes have revealed that element creation continues at a vigorous pace throughout the observable universe. The James Webb Space Telescope has detected evidence of heavy element production in some of the most distant and ancient galaxies, showing that stellar nucleosynthesis began operating very early in cosmic history. At the same time, gravitational wave detectors like LIGO have opened a new window into element creation by detecting the space-time ripples produced by neutron star collisions. These observations confirm that such mergers are indeed significant sources of the heaviest elements, just as theoretical models predicted. The story of the elements is also intimately connected to the broader story of cosmic evolution. The same physical processes that govern element creation in stars also drive the formation of galaxies, the growth of black holes, and the large-scale structure of the universe. Understanding stellar nucleosynthesis, therefore, provides insights into how the cosmos as a whole has evolved from its simple beginnings into the complex, structured universe we observe today. Dark matter, the mysterious substance that makes up most of the universe's mass, plays a crucial but invisible role in this story. Although dark matter particles do not participate directly in nuclear reactions, their gravitational influence determines how and where ordinary matter can collect to form stars. The cosmic web of dark matter provides the scaffolding on which galaxies form and evolve, ultimately controlling the rate and location of element creation throughout the universe. Dark energy, the even more mysterious force driving the accelerated expansion of the universe, affects the story of element creation on the largest scales. By causing the universe to expand ever more rapidly, dark energy limits how much time is available for galaxies to form new stars and create heavy elements. In the far future, when dark energy has stretched the universe to enormous scales, star formation will eventually cease, bringing the era of active element creation to an end. But that ending is still trillions of years in the future. For now, the cosmic story of element creation continues to unfold across the universe. New stars are being born from gas clouds enriched by previous stellar generations. Massive stars are reaching the ends of their lives and preparing to explode as supernova. Neutron stars formed in ancient explosions continue their slow gravitational dance toward eventual collision and merger. Each of these events adds new elements to the cosmic inventory, increasing the chemical complexity of the universe and expanding the range of possible structures and phenomena. The process that began with the simple fusion of hydrogen into helium in the first stars has now produced a universe rich in chemical diversity, capable of forming everything from planets and oceans to living cells and conscious minds. Looking up at the night sky, we can see this ongoing process of element creation with our own eyes. The red glow of star-forming nebulae reveals hydrogen gas being energized by the ultraviolet light of newly formed massive stars. These young giants are beginning their own careers of nuclear fusion, converting primordial hydrogen into heavier elements that will eventually be dispersed into space. The blue and white stars we see scattered across the constellations are massive stellar furnaces operating at tremendous temperatures, actively engaged in the synthesis of carbon, oxygen, silicon, and iron in their cores. Though they appear as mere points of light to our eyes, each one is a cosmic factory working around the clock to transform simple atoms into complex ones. Sometimes we are fortunate enough to witness the explosive culmination of this process. When astronomers detect a new supernova in a distant galaxy, we are seeing the moment when billions of years of stellar evolution reach their dramatic climax. For a few weeks, that single exploding star outshines billions of normal stars, announcing to the universe that a new batch of heavy elements has been created and released into space. Occasionally, these cosmic explosions happen close enough to Earth that we can study them in extraordinary detail. In 1987, a supernova exploded in the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way. This event, designated SN 1987A, provided astronomers with an unprecedented opportunity to observe stellar nuclear synthesis in action. The light from SN 1987A told the story of element creation in exquisite detail. The initial explosion showed the characteristic signatures of hydrogen and helium from the star's outer layers. As the shock wave penetrated deeper into the stellar debris, it revealed successive layers rich in carbon, oxygen, silicon, and finally iron from the star's core. Radioactive isotopes of nickel and cobalt, created in the final moments of the explosion, powered the supernova's glow for months afterward as they decayed into stable iron. Even today, more than 30 years after the explosion, astronomers continue to monitor SN 1987A as it evolves. The expanding shockwave has now collided with material that the star ejected thousands of years before its final explosion, creating a glowing ring of hot gas around the supernova site. This ongoing light show provides a real-time view of how stellar elements mix with the interstellar medium, beginning their journey toward eventual incorporation into new stars and planets. Such detailed observations help us understand not just how elements are created, but how they are distributed throughout space. The process is not uniform. Some directions from the explosion site receive more heavy elements than others, and the mixing with surrounding gas happens over thousands of years. This patchy distribution means that some regions of space become more enriched with heavy elements than others, influencing where future generations of stars and planets can form. The complexity of this element distribution is one reason why the search for potentially habitable planets is so challenging. A planet might form in a region that happened to receive an unusually large amount of heavy elements from a nearby ancient supernova, making it rich in the materials needed for rocky planet formation. Complex chemistry. Another planet might form in a region that missed most of the heavy element enrichment, leaving it depleted in the materials necessary for life. These considerations have led astronomers to think about galactic habitable zones, regions within galaxies where conditions are most favorable for the development of complex life. These zones need to be close enough to the galactic center to benefit from heavy element enrichment by multiple generations of stars, but far enough away to avoid the disruptive effects of supernova explosions and other violent events. Our solar system appears to be located within such a galactic habitable zone. We are positioned about halfway out from the galactic center, in a relatively quiet region between major spiral arms. This location has allowed us to benefit from billions of years of element creation by previous stellar generations, while avoiding the most extreme environments that might disrupt planetary development or sterilize existing life. The concept of galactic habitable zones also helps explain why life might be rare in the universe, even if the basic chemistry of life is universal. Many regions of galaxies may simply lack the heavy element abundance necessary for rocky planet formation and complex biochemistry. life might be confined to relatively small zones within certain types of galaxies, making it far less common than we might otherwise expect. These ideas are being tested by ongoing astronomical surveys that map the distribution of heavy elements throughout our galaxy and others. By studying the spectra of stars in different galactic regions, astronomers can determine their heavy element content and trace how stellar nucleosynthesis has enriched different parts of the galaxy over time. The results of these surveys reveal a complex picture of galactic chemical evolution. The inner regions of our galaxy show evidence of rapid early enrichment by massive stars and supernova. The outer regions have been enriched more slowly and less completely. Between these extremes lies a zone of moderate heavy element abundance that includes our solar system, possibly the galactic sweet spot for life. Similar surveys of other galaxies reveal that this pattern of chemical evolution is common throughout the universe. Elliptical galaxies, which experienced rapid bursts of star formation early in their history, tend to be uniformly enriched with heavy elements, but have little ongoing star formation. Spiral galaxies like our own show more complex patterns of enrichment, with heavy elements concentrated in the spiral arms where most star formation occurs. Irregular galaxies and galaxy mergers show the most dramatic variations in heavy element abundance. When galaxies collide and merge, they trigger intense bursts of star formation and supernova activity that can rapidly change the chemical composition of entire galactic regions. These events may create new galactic habitable zones while destroying others. Understanding these large-scale patterns of element creation and distribution helps us place our own existence in cosmic context. We are not just made of star stuff, we are made of star stuff that was created in a particular place and time, distributed in a particular way, and assembled into planets and living beings under very specific conditions. The elements in our bodies carry information about all of these cosmic processes. The isotopic ratios of different elements can tell us about the specific types of stars and stellar explosions that created them. For example, the ratio of different oxygen isotopes in meteorites reveals details about the stellar environments where those atoms were formed billions of years ago. Some elements in our bodies may have formed in multiple stellar environments before eventually becoming part of Earth. A carbon atom in your DNA might have been created first in the core of an intermediate mass star, ejected into space when that star became a planetary nebula, incorporated into a new star that later exploded as a supernova, mixed with supernova-produced elements in the interstellar medium, and finally condensed into the solid materials that formed our solar system. This complex history is written into the atomic structure of every element. Advanced laboratory techniques can now read parts of this stellar history by analyzing tiny samples of meteorites, which preserve some of the most primitive materials in our solar system. These ancient rocks contain microscopic grains that actually formed in the atmospheres of dying stars and survived the formation of our solar system unchanged. By studying these pre-solar grains, scientists can directly examine matter that was created in specific stellar environments billions of years ago. The isotopic compositions of these grains often differ dramatically from the average values found in solar system materials, revealing their exotic origins in supernova, red giant stars, and other stellar environments. These studies provide a remarkably direct connection between laboratory science and stellar astrophysics. When a scientist analyzes a presolar grain under a microscope, they are literally examining a piece of an ancient star that died before our solar system formed. The same nuclear reactions that we study in particle accelerators and observe in distant stellar spectra created the atoms in these microscopic stellar artifacts. The story of the elements therefore connects the largest scales of space and time with the most intimate details of our physical existence. The same cosmic processes that govern the evolution of galaxies and the formation of stars also determine the chemistry of our cells and the thoughts in our minds. We are walking, thinking embodiments of cosmic evolution, temporary arrangements of stellar matter that have somehow gained the ability to understand their own origins. This understanding has profound implications for how we view ourselves and our place in the universe. We are not separate from the cosmos, but integral parts of its ongoing evolution. The elements that make up our bodies will not remain bound together forever eventually. They will be recycled back into the environment, and from there into new generations of stars, planets, and perhaps even new forms of life we cannot yet imagine. The calcium in our bones may someday become part of a coral reef in a distant ocean. The iron in our blood may find its way into the core of a forming planet around a young star. The carbon in our DNA may become incorporated into the organic molecules of alien life forms in some far future epoch. In this sense, we are temporary custodians of stellar matter, privileged to participate briefly in the universe's ongoing story of chemical evolution. This cosmic recycling operates on timescales that dwarf human experience. The elements in your body have already participated in countless cycles of stellar death and rebirth. They have been part of countless stars, planets, and perhaps even other living beings over the billions of years since they were first created. The oxygen atom you just breathed may have been part of a dinosaur, an ancient fern, or a drop of primordial ocean water. Its journey through time connects you to every era of Earth's history and beyond. Even more remarkably, some of the heaviest elements in your body may have been created in neutron star collisions that happened when the universe was much younger. The gold in any jewelry you might be wearing was forged in conditions so extreme that they warp space-time itself. The iodine in your thyroid gland was created when two stellar remnants, each more massive than our Sun but compressed to the size of a city, crashed together at a significant fraction of the speed of light. These elements have traveled unimaginable distances to become part of you. They may have originated in explosions that occurred in distant parts of our galaxy, or even in other galaxies entirely. Over billions of years, they have drifted through the vacuum of interstellar space, sometimes alone as individual atoms, sometimes bound together in molecules or incorporated into cosmic dust grains. Their journey has taken them through environments of every conceivable extreme. They have experienced the near absolute zero of interstellar space and the million-degree heat of stellar coronas. They have been accelerated by supernovae shockwaves and decelerated by magnetic fields. They have participated in the formation and destruction of countless molecular clouds, witnessed the birth and death of stars, and perhaps been present during the collision of galaxies. The complexity of this journey is staggering to contemplate. Each atom in your body has its own unique history, its own pathway through space and time that eventually led to its incorporation into a living being. The phosphorus atoms in your DNA may have followed completely different routes through the galaxy before eventually coming together in the molecular machinery of your cells. Some atoms may have taken relatively direct paths, being incorporated into our solar system soon after their creation in nearby stellar explosions. Others may have wandered the galaxy for billions of years, passing through multiple episodes of star formation and stellar death before finally ending up on Earth. A few may even be immigrants from other galaxies, carried here by intergalactic winds or the gravitational interactions of galactic encounters. This cosmic perspective on the elements reveals that Earth itself is not a closed system, but an active participant in the galaxy's ongoing chemical evolution. Our planet continues to accumulate new stellar material from space in the form of meteorites, cosmic dust, and even individual atoms carried by the solar wind. At the same time, atmospheric escape processes are slowly returning some of Earth's lightest elements to space, where they rejoin the cosmic circulation. The balance between these processes has changed throughout Earth's history. In the planet's early days, when the solar system was still full of debris from its formation, the input of new material was much higher. Massive asteroid and comet impacts delivered large quantities of stellar elements to Earth's surface, including much of the water in our oceans and the organic compounds that may have contributed to the origin of life. Today, the input is much gentler but still ongoing. Every day, Earth gains approximately 100 tons of mass from cosmic dust and small meteorites. This may seem insignificant compared to our planet's total mass, but over millions and billions of years, it represents a substantial exchange of material with the cosmos. We are still accreting star stuff, still participating in the universe's element circulation system. This ongoing exchange means that the story of the elements is not just ancient history, but a continuing process that affects us today. The cosmic dust settling on Earth right now contains elements created in stellar explosions that may have occurred millions of years ago. Some of this material will eventually make its way into the food chain and become incorporated into living organisms, including humans. In a very literal sense, we are still being built from stellar material. The elements in our bodies are not fixed and permanent, but constantly being replaced through the processes of metabolism, growth, and cellular repair. The carbon atoms in your body are replaced on a timescale of years, the calcium in your bones over decades. As these atoms are replaced, some of them may be recent arrivals from space, stellar matter that has only just completed its billion-year journey from some ancient supernova to become part of a living being. This ongoing replacement means that you are not exactly the same collection of atoms you were a few years ago. While the patterns and structures that define you have remained relatively constant, the actual physical matter has been slowly exchanged with the environment. You are more like a persistent pattern in the flow of stellar elements than a fixed collection of atoms. This view of human identity as a temporary arrangement of cosmic matter echoes ancient philosophical traditions while being grounded in modern scientific understanding. We are indeed connected to the cosmos in the most fundamental way possible. We are made from it, we are part of it, and we will eventually return to it. Our existence represents a brief moment of organization and self-awareness in the universe's ongoing evolution toward greater complexity. The elements themselves, however, are far more permanent than the structures they temporarily form. The carbon atoms in your DNA will survive long after your death, potentially participating in countless future arrangements of matter. They may become part of other living beings, or they may be incorporated into rocks, oceans, or even future planets. On cosmic timescales, the atoms are the persistent entities, while organisms like ourselves are fleeting patterns. This realization can be both humbling and inspiring. Humbling because it reminds us that our individual existence is temporary in cosmic terms. Inspiring because it connects us to something far greater than ourselves, the entire history and future evolution of the universe. We are not isolated beings struggling alone in an indifferent cosmos, but integral participants in the grandest story ever told. The story of the elements also reveals the profound interconnectedness of all matter in the universe. The calcium in your bones and the calcium in distant rocky planets were created by the same stellar processes. The iron in your blood and the iron in meteorites scattered throughout the solar system originated in the same supernova explosions. Every atom of every element connects us to every other part of the cosmos where that element exists. This cosmic connectivity extends beyond our solar system to encompass the entire galaxy and beyond. The heavy elements in your body link you to every planet, every star, and every living being that shares those same stellar-forged materials. If life exists elsewhere in the universe, it too must be built from elements created in stellar cores and distributed by supernova explosions. In this sense, all life in the cosmos would share a common elemental heritage. Modern astronomy continues to reveal new details about this shared cosmic heritage. Spectroscopic studies of distant stars and galaxies show that the same nuclear processes that created the elements in our bodies are operating throughout the observable universe. The ratio of carbon to oxygen, the abundance of iron relative to hydrogen, the presence of trace elements like lithium. These cosmic chemical signatures are remarkably consistent across vast distances. Time. This consistency suggests that stellar nuclear synthesis operates according to universal physical laws that produce similar results everywhere in the cosmos. The elements that make life possible on Earth are not unique or special. They are natural products of stellar evolution that should exist anywhere. Stars have been shining long enough to enrich their environments with heavy elements. At the same time, the distribution of these elements is not perfectly uniform. Local variations in stellar history, supernova rates, and galactic dynamics create regions with different element abundances. These variations may play a crucial role in determining where life can emerge and thrive. Understanding the cosmic distribution of life-essential elements therefore becomes a key component in the search for life beyond Earth. Recent discoveries of potentially habitable exoplanets have highlighted the importance of stellar composition in determining planetary properties. Planets orbiting stars with high heavy element abundances are more likely to be rocky worlds with complex surface chemistry. Planets around metal-poor stars may be primarily gas giants or ice worlds lacking the solid surfaces and chemical diversity needed for Earth-like life. Even among rocky planets, the specific mix of elements inherited from stellar nucleosynthesis can dramatically affect habitability. A planet with too little iron may lack a magnetic field to protect it from cosmic radiation. A planet with too little carbon may be unable to support carbon-based life. A planet with too much uranium or other radioactive elements may experience lethal levels of radiation. These considerations have led astrobiologists to think carefully about the cosmic prerequisites for life. It is not enough for a planet to be in the right temperature zone around its star. It must also be composed of the right mix of elements, and those elements must have been delivered through the right sequence of stellar and chimera, planetary processes. The story of the elements is therefore inseparable from the story of life itself. Looking toward the future, the ongoing process of stellar nucleosynthesis will continue to enrich the universe with heavy elements for trillions of years to come. Each new generation of stars will add to the cosmic inventory of complex atoms, creating ever greater opportunities for chemical complexity and perhaps life. The universe is still very young in terms of stellar evolution. Most of the stars that will ever exist have not yet been born. This means that the golden age of element creation may still lie ahead. Future generations of stars forming from gas clouds enriched by billions of years of stellar evolution may create conditions even more favorable for complex chemistry and life than exist today. The universe of the far future may be far richer in heavy elements than the cosmos we observe today. At the same time, the accelerating expansion of the universe driven by dark energy will eventually limit how much longer this process can continue. As space expands, galaxies will become increasingly isolated from each other, and the raw materials for star formation will be gradually depleted. Eventually, the era of active stellar nuclear synthesis will come to an end, and no new heavy elements will be created. But that ending is still incredibly far in the future, so distant that it is difficult to express in any meaningful way. For now, and for countless generations to come, the cosmic story of element creation continues. New stars are being born, massive stars are preparing to explode, and neutron stars are spiraling toward collision. Each of these events adds new chapters to the story that began with the first stars and will continue until the last stars burn out. In contemplating this vast cosmic perspective, we gain a new appreciation for the remarkable circumstances that led to our existence. The elements in our bodies required billions of years of stellar evolution to create. They needed to be dispersed through space by violent explosions, collected into new stellar systems, and assembled into rocky planets under precisely the right conditions. Finally, they needed to organize themselves into the complex chemistry that makes life possible. The probability that any particular collection of atoms would end up as part of a conscious being capable of understanding its own cosmic origins is vanishingly small. Yet here we are, temporary arrangements of stellar matter that have somehow gained the ability to contemplate the universe that created us. We are the cosmos becoming self-aware, the universe developing the capacity to understand its own history and evolution. This perspective suggests that consciousness itself may be one of the most remarkable products of cosmic evolution. Just as stars transform simple hydrogen into complex heavy elements, biological evolution has transformed simple stellar matter into thinking beings capable of scientific understanding. We represent a new phase in the universe's development toward greater complexity and organization. The neural networks in our brains, built from stellar carbon, nitrogen, and phosphorus, have become sophisticated enough to decode the nuclear physics that created those very elements. Our eyes, constructed from stellar matter, can observe distant galaxies where element creation is still ongoing. Our instruments, fabricated from stellar iron and silicon, can detect the gravitational waves produced by neutron star collisions billions of light years away. In this sense, the universe has developed the ability to study itself through us. When we observe distant supernova or analyze the spectrum of stellar light, we are enabling the cosmos to understand its own processes of creation and evolution. The atoms in our scientific instruments are investigating the stellar explosions that created them. The elements in our bodies are learning about their own cosmic origins. This recursive relationship between observer and observed, between the products of stellar nuclear synthesis and the process itself, reveals the profound unity underlying all of existence. We are not external observers studying a foreign universe, but internal participants in cosmic evolution, examining our own history and destiny. The story of the elements therefore becomes not just a scientific account of nuclear physics and stellar evolution, but a profound meditation on existence itself. In learning where the elements came from, we learn where we came from. In understanding how stars create and distribute heavy atoms, we understand the processes that made our own existence possible. Every element tells a story of cosmic evolution. Hydrogen speaks of the primordial fireball that began it all. Helium recalls the first few minutes when the universe was a nuclear reactor operating on cosmic scales. Carbon remembers the patient nuclear fusion in stellar cores that built the foundation for organic chemistry. iron bears witness to the violent collapse of massive stellar cores. Gold carries memories of neutron star collisions that shook space-time itself. Together, these elements compose the material basis for everything we know: stars, planets, oceans, mountains, forests, animals, and human beings. They provide the physical foundation for all of chemistry, all of biology, all of consciousness. Without the cosmic processes that created and distributed the heavy elements, the universe would remain a simple mixture of hydrogen and helium, incapable of supporting the rich phenomena we observe today. The elements also provide a common language that connects all of science. The same periodic table that describes the atoms in our bodies also describes the composition of distant stars and galaxies. The same nuclear physics that governs stellar fusion also explains radioactive decay in Earth's interior. The same chemical bonds that hold our DNA together also determine the properties of materials throughout the cosmos. In this universality of physical law and chemical behavior, we glimpse something profound about the nature of reality itself. Despite the vast scales of space and time that separate us from other parts of the universe, we are connected by shared physical principles and common material origins. The elements provide both the substance and the syntax for the cosmic story of which we are part. As we continue to explore the universe with ever more sophisticated instruments, we are adding new chapters to the story of the elements. Space telescopes reveal element creation happening in real time in distant galaxies. Gravitational wave detectors allow us to hear the cosmic collisions that forge the heaviest elements. Particle accelerators let us recreate and study the nuclear reactions that power stars. Each new discovery adds detail to our understanding of how the elements formed and evolved. We now know that different types of stars contribute different elements to the cosmic inventory. We understand that supernova explosions occur in several distinct varieties, each with its own characteristic pattern of element production. We have learned that neutron star mergers are essential for creating the heaviest elements, and that these mergers may be relatively rare events in cosmic history. These discoveries also reveal that the story of the elements is more complex and nuanced than we once imagined. Element creation is not a simple, uniform process, but a diverse array of phenomena operating under different conditions throughout space and time. The cosmic chemical evolution that led to our existence involved an intricate interplay of stellar physics, galactic dynamics, and cosmic history. Understanding this complexity helps us appreciate how remarkable our existence truly is. We are not just made of star stuff, but of star stuff that was created, processed, and delivered through a precise sequence of cosmic events spanning billions of years. The slightest changes in stellar physics, galactic evolution, or cosmic history might have prevented the chemical conditions necessary for life from ever developing. Yet here we are, living proof that the universe is capable of creating beings complex enough to understand their own origins. In US, the cosmos has developed not just self-awareness, but also the capacity for wonder, curiosity, and scientific investigation. We represent the universe's attempt to comprehend itself, to trace its own history from the simplest beginnings to the most complex present. This perspective transforms our understanding of what it means to be human. We are not accidental byproducts of cosmic evolution, but perhaps inevitable consequences of the universe's tendency toward greater complexity and organization. Our ability to understand stellar nucleosynthesis may represent a natural development in cosmic evolution, as inevitable as the formation of heavy elements themselves. In contemplating the origin of the elements, we are therefore contemplating our own deepest nature. We are temporary arrangements of stellar matter that have somehow acquired the capacity for self-reflection and cosmic understanding. We are walking embodiments of the universe's creative potential, living demonstrations of what simple matter can become given enough time and the right conditions. The elements in our bodies connect us not only to the stars that created them, but to the entire future evolution of the cosmos. When we die, those elements will continue their cosmic journey, perhaps eventually becoming part of new stars, new planets, and new forms of life. In this sense, we are temporary custodians of stellar matter, privileged to participate briefly in the universe's ongoing story of chemical and biological evolution. This cosmic perspective on human existence suggests that our lives have meaning and significance far beyond their brief duration. We are the universe becoming conscious of itself, the cosmos developing the ability to understand its own history and contemplate its future. Through our scientific investigations and philosophical reflections, we enable the elements themselves to learn about their own origins and destinies. In the end, the story of the elements is our story. It is the account of how simple matter became complex, how unconscious atoms became conscious beings, how the universe developed the capacity to understand itself. We are made of star stuff, not just in a physical sense, but in the deepest possible way. We are the cosmos awakened to its own existence, stellar matter transformed into mind and consciousness. The next time you look up at the night sky, remember that you are not simply observing the universe from the outside. You are part of it, made from it, connected to every star you see by the atoms in your body. The iron in your blood was forged in stellar cores. The oxygen in your lungs was created in massive stellar explosions. The carbon in your DNA was manufactured in the patient nuclear furnaces of countless ancient suns. You are a temporary constellation of stellar matter, organized for a brief moment into the pattern we call a human being. Your thoughts are the universe thinking about itself. Your wonder at the cosmos is the cosmos marveling at its own existence. Your quest to understand the origin of the elements is the elements themselves seeking to comprehend their own remarkable story. In this profound sense, we are all children of the stars, born from stellar death and destined to return to the cosmic circulation of matter and energy. We are participants in the greatest story ever told, the story of how the universe evolved from simplicity to complexity, from unconsciousness to awareness, from a handful of fundamental particles to the rich tapestry of existence we observe today. The elements are not just the building blocks of matter, but the alphabet of cosmic evolution, the vocabulary with which the universe writes the story of its own development. In learning to read this cosmic scripture, we discover not just how the world is made, but what it means to exist as conscious beings in a universe capable of creating its own chroniclers and interpreters. We are made of star stuff, and in US, the stars have learned to dream. This cosmic dreaming takes many forms. When we create art, we are arranging stellar carbon and other elements into patterns that express beauty and meaning. When we compose music, we are using stellar matter organized into brains and instruments to create vibrations that touch the soul. When we write poetry about the night sky, we are enabling the universe to celebrate its own magnificence through words made possible by stellar nucleosynthesis. The very act of scientific discovery represents a form of cosmic self-recognition. When astronomers decode the spectrum of a distant star and determine its elemental composition, they are using stellar elements in their own bodies and instruments to analyze stellar elements in space. The silicon in their detectors reads the silicon signatures in starlight. the iron in their blood resonates with the iron absorption lines in stellar spectra. This recursive relationship between observer and observed pervades all of astronomy and indeed all of science. The same quantum mechanics that governs fusion reactions in stellar cores also governs the behavior of electrons in the computers we use to model those reactions. The same electromagnetic forces that bind atomic nuclei together also enable our eyes to detect the photons that carry information about those nuclei across interstellar space. In studying the elements, we are therefore engaged in an act of cosmic self-examination. The universe is literally using part of itself to understand other parts of itself. This is perhaps the most remarkable aspect of the entire story, that matter organized into human beings has become capable of tracing its own history back to the nuclear furnaces where it was born. Consider the extraordinary journey that brought the elements in your body to this moment of understanding. Billions of years ago, in the core of some long-dead star, protons and neutrons came together under conditions of unimaginable heat and pressure. The nuclear forces that bind atomic nuclei overcame the electromagnetic forces that would push them apart, creating the first heavy elements through stellar fusion. These newly minted atoms were dispersed into space by stellar winds or supernova explosions, beginning a journey through the galaxy that would last millions or billions of years. They drifted through molecular clouds, were incorporated into new generations of stars, and perhaps were processed again through additional cycles of stellar nucleosynthesis. Eventually, they became part of the disk of gas and dust from which our solar system formed. In the swirling chaos of the early solar system, these atoms were incorporated into the rocky materials that would eventually become Earth. Through geological processes operating over hundreds of millions of years, they were concentrated and processed, eventually becoming available for biological systems. Through the chemistry of life, they were assembled into the complex molecules that make cellular function possible. Finally, through the processes of evolution and development, they became part of a human brain capable of contemplating their own cosmic origins. The neural networks built from these stellar atoms developed the capacity for abstract thought, scientific reasoning, and philosophical reflection. In you, these ancient stellar products have achieved something unprecedented: the ability to understand and appreciate their own remarkable journey. This transformation from stellar nuclei to conscious thought represents one of the most extraordinary progressions in cosmic history. It required not just the creation of heavy elements through stellar processes, but their organization into increasingly complex structures through planetary, chemical, and biological evolution. Each stage of this progression was necessary, but not sufficient for the emergence of consciousness. The path from stellar nucleosynthesis to human awareness involved countless contingencies and near-impossible coincidences. The right stars had to explode at the right times and places to enrich the interstellar medium with heavy elements. Our solar system had to form in a region of the galaxy with the right chemical composition and relatively stable conditions. Earth had to develop the right combination of atmosphere, oceans, and geological activity to support complex chemistry. Even then, the emergence of life required an additional series of remarkable developments. Simple organic molecules had to organize themselves into self-replicating systems. These early life forms had to survive in hostile conditions and gradually develop the biochemical machinery needed for metabolism, growth, and reproduction. Over billions of years, evolution had to transform single-celled organisms into complex multicellular life, capable of nervous systems and, ultimately, consciousness. Each of these steps involved the stellar elements being organized into progressively more complex and sophisticated arrangements. The same carbon atoms that began as simple nuclei in stellar cores eventually became part of DNA molecules encoding genetic information. The same nitrogen atoms forged in massive stars became essential components of proteins and neurotransmitters. The same phosphorus atoms created in supernova explosions became integral parts of cellular energy systems and neural membranes. What makes this progression even more remarkable is that it appears to be an ongoing process. Human consciousness may not represent the final stage of cosmic evolution, but rather an intermediate step toward even greater complexity and understanding. Through our scientific and technological developments, we are creating new forms of information processing and new ways of organizing matter that may eventually transcend the limitations of biological castes. Consciousness. Our computers and artificial intelligence systems represent new ways of arranging stellar elements into patterns capable of computation and problem solving. Our global communication networks create connections between human minds that approach something like a planetary consciousness. Our space exploration efforts are beginning to spread stellar matter beyond its planet of origin, potentially setting the stage for new forms of cosmic evolution. In this sense, we may be witnessing the early stages of the next great transition in cosmic history, the emergence of technological intelligence that can consciously direct its own evolution and spread throughout the part. Cosmos. Just as biological evolution transformed simple stellar matter into conscious beings, technological evolution may transform conscious beings into something even more remarkable. This possibility gives new meaning to our role as temporary arrangements of stellar matter. We may not just be the universe becoming aware of itself, but the universe developing the tools and capabilities needed for its next phase of evolution. Through our science and technology, we are enabling the cosmos to transcend the limitations that have confined it to isolated pockets of complexity on scattered planets. Our space missions carry stellar elements to new locations throughout the solar system. Our radio telescopes and interstellar messages represent attempts by the universe to communicate with other instances of itself across vast distances. Our efforts to understand and potentially modify our own genetic code and consciousness represent the cosmos developing the ability to direct its own future evolution. These developments are still in their infancy, but they suggest that the story of the elements may be entering a new chapter. For billions of years, stellar nuclear synthesis and biological evolution have been the primary drivers of increasing cosmic complexity. Now, for the first time, conscious beings made of stellar matter are beginning to take active control of how that matter is organized and used. This transition from passive to active evolution represents a fundamental shift in cosmic history. Previously, the elements could only be rearranged through the blind processes of stellar physics, chemistry, and biological natural selection. Now they can be consciously manipulated and organized according to deliberate plans and purposes. The universe has developed the ability to engineer its own future. The implications of this development are profound and largely unpredictable. Conscious beings with advanced technology might be able to create new elements not found in nature, extending the periodic table beyond what stellar processes can achieve. They might develop new ways of organizing matter that produce forms of consciousness and intelligence far beyond current human capabilities. They might even be able to influence the large-scale processes of cosmic evolution itself. Advanced civilizations might find ways to extend the lifetimes of stars, trigger controlled stellar explosions to enrich interstellar space with heavy elements, or even create new stars and planetary doubly, systems tailored for specific purposes. The cosmic story of element creation and distribution might become a consciously directed process rather than a natural one. These possibilities may seem like science fiction, but they represent logical extensions of trends already visible in human development. We have already learned to create elements that don't exist naturally on Earth through particle accelerators and nuclear reactors. We have developed technologies for manipulating matter at the atomic and molecular level. We are beginning to understand and modify the genetic code that governs biological development. Given enough time and continued technological progress, it seems inevitable that conscious beings will develop capabilities that approach or exceed those of natural, stellar, and cosmic processes. The same intelligence that allowed us to understand stellar nucleosynthesis may eventually allow us to surpass it, creating new forms of matter and energy that extend far beyond what nature has achieved. This prospect transforms our understanding of cosmic significance. We are not just temporary arrangements of stellar matter destined to return to the cosmic circulation unchanged. We are potentially the means by which the universe transcends its current limitations and enters entirely new phases of evolution and development. The elements in our bodies may therefore represent more than just the products of past cosmic evolution. They may be the raw materials for future cosmic transformation. The stellar carbon, nitrogen, and oxygen that make our consciousness possible may eventually be reorganized into forms of intelligence and capability that we cannot currently imagine. This possibility gives added urgency and importance to our current scientific endeavors. Every advance in our understanding of physics, chemistry, and biology brings us closer to the capabilities needed to take conscious control of cosmic evolution. Every technological development increases our ability to organize stellar matter in new and more sophisticated ways. At the same time, this prospect carries enormous responsibility. If we are indeed the universe's means of transcending its current limitations, then our choices and actions have consequences that extend far beyond our individual lives or even our species' survival. We are potential stewards of cosmic evolution itself, entrusted with the stellar matter from which future forms of complexity and consciousness might emerge. This responsibility extends to how we treat our planet and each other. Earth represents the universe's successful experiment in organizing stellar matter into a biosphere capable of producing conscious beings. Destroying this achievement through environmental degradation or warfare would not just be a tragedy for humanity, but a cosmic setback in the universe's journey toward greater complexity and understanding. Similarly, our efforts to understand the cosmos and develop new technologies represent cosmic investments in the future. Scientific research and education are not just human activities, but processes by which the universe increases its own self-knowledge and capabilities. Supporting these endeavors is therefore a form of cosmic service, helping the universe achieve its apparent tendency toward greater organization and awareness. This perspective also transforms our understanding of what it means to live a meaningful life. We are not isolated individuals struggling alone in an indifferent universe, but active participants in the cosmos' ongoing evolution toward greater complexity and consciousness. Every act of learning, creating, or building contributes to this cosmic project. Every moment of wonder or understanding represents a victory for the universe's journey towards self-awareness. Even our most mundane activities take on cosmic significance when viewed from this perspective. When you eat, you are participating in the chemical processes that enable stellar matter to organize itself into living systems. When you breathe, you are cycling stellar oxygen through the biological machinery that makes consciousness possible. When you think, you are enabling the universe to contemplate its own existence through neural networks built from stellar elements. This cosmic perspective on daily life can provide a sense of meaning and purpose that transcends individual concerns. We are not just living for ourselves, but serving as temporary custodians and organizers of stellar matter, but has spent billions of years journeying through space to reach this point of self-awareness. Our lives represent brief moments in the universe's long project of understanding and transforming itself. The relationships we form with other people take on added significance when viewed as connections between different arrangements of stellar matter. When you love someone, you are creating bonds between collections of atoms that were forged in stellar cores and dispersed by cosmic explosions. When you share knowledge or ideas, you are enabling the universe to communicate with itself across different organizations of the same fundamental stellar material. Human culture and civilization represent collective efforts to organize and preserve the universe's growing self-knowledge. Our libraries, museums, and educational institutions are repositories of cosmic understanding, places where the universe stores information about its own nature and history. Our arts and philosophies represent attempts by the cosmos to express and appreciate its own beauty and meaning through conscious beings made of stellar matter. Even our conflicts and struggles can be understood as part of the universe's ongoing effort to organize itself more effectively. Competition and cooperation, conflict and collaboration, represent different strategies for arranging and coordinating the behavior of conscious stellar matter. Through trial and error, success and failure, the cosmos is gradually learning how to organize itself into more stable and capable forms. This evolutionary perspective suggests that our current human civilization, remarkable as it is, represents only an early experiment in conscious cosmic organization. Future arrangements of stellar matter may be far more sophisticated and capable than current human societies. They may develop forms of cooperation, communication, and collective intelligence that make our current achievements seem primitive by comparison. Yet we are the foundation on which these future developments will be built. The scientific knowledge we accumulate, the technologies we develop, the cultural achievements we create, all of these represent investments in the universe's future capabilities. We are laying the groundwork for forms of cosmic consciousness and capability that may eventually transform the entire nature of existence. This long-term perspective can provide comfort and meaning even in the face of individual mortality. Though our personal arrangements of stellar matter are temporary, the knowledge and capabilities we help develop may persist and contribute to cosmic evolution for billions of years to come. Through our contributions to science, technology, culture, and human development, we participate in projects that extend far beyond our individual lifespans. The elements in our bodies will eventually be recycled back into the environment, but the information and capabilities we help create may become permanent parts of the universe's growing self-knowledge. In this sense, consciousness may represent a means by which the cosmos creates something approaching immortality, not for individual beings, but for the accumulated understanding and capability of consciousness, matter itself. This possibility gives new meaning to the ancient human quest for immortality and transcendence. Rather than seeking to preserve our individual arrangements of stellar matter indefinitely, we might focus on contributing to the universe's collective journey toward greater consciousness and capability. By helping to advance cosmic self-understanding and organization, we participate in something that may indeed be immortal. The search for extraterrestrial intelligence takes on added significance from this perspective. If consciousness represents the universe's means of understanding and directing its own evolution, then the discovery of other conscious beings would reveal additional experiments in cosmic self-organization. Each independently evolved form of consciousness would represent a different approach to organizing stellar matter into self-aware systems. Contact with alien intelligence would therefore be more than just a meeting between different species. It would be an encounter between different experiments in cosmic consciousness. By comparing and combining different approaches to organizing stellar matter into conscious systems, the universe might be able to achieve forms of awareness and capability that exceed what any single species could progress, develop alone. This possibility suggests that the search for extraterrestrial intelligence is not just a scientific curiosity, but a cosmic imperative. The universe may require multiple independent experiments in consciousness to achieve its full potential for self-understanding and self-direction. Our efforts to detect and communicate with alien civilizations may therefore represent essential steps in cosmic evolution. At the same time, the apparent rarity of detectable alien civilizations suggests that the emergence of consciousness from stellar matter is an extraordinary achievement that should not be taken for granted. Each instance of conscious life may represent a precious and irreplaceable experiment in cosmic self-organization. The loss of any conscious civilization would therefore be a tragedy not just for the beings involved, but for the universe's overall project of self-development. This perspective reinforces the importance of preserving and protecting conscious life wherever it exists. Every conscious being represents a unique arrangement of stellar matter that has achieved the remarkable capability of self-awareness and cosmic understanding. The loss of such arrangements reduces the universe's total capacity for self-knowledge and self-direction. The preservation of consciousness also requires the preservation of the conditions that make consciousness possible. This includes not just the immediate biological and environmental requirements, but the larger cosmic conditions that enable heavy element formation and distribution. The continuation of stellar nucleosynthesis, the stability of galactic environments, and the long-term evolution of the universe all affect the future prospects for conscious life. In the very long term, the universe faces challenges that may threaten the continued existence of consciousness. The accelerating expansion driven by dark energy will eventually isolate galaxies from each other and make new star formation impossible. The depletion of hydrogen fuel will gradually extinguish existing stars. The decay of protons, if it occurs, will eventually dissolve all atomic nuclei back into simpler particles. These cosmic challenges suggest that consciousness may need to find ways to transcend its current dependence on stellar nuclear synthesis and biological processes. Advanced civilizations may need to develop new sources of energy and new forms of information processing that can survive the death of stars and the decay of atoms. The universe's project of self-understanding may require conscious beings to find ways to preserve and continue their existence, even as the cosmos evolves towards simpler and more dispersed states. This ultimate challenge gives cosmic significance to our current efforts to understand fundamental physics and develop advanced technologies. The knowledge we gain about the nature of matter, energy, space, and time may eventually be essential for consciousness to survive the long-term evolution of the universe. Our current scientific research may therefore be laying the foundation for the cosmic preservation of awareness itself. The possibility that consciousness might find ways to transcend cosmic evolution adds a new dimension to the story of the elements. The stellar matter that makes us possible may eventually be transformed into forms of organization that no longer depend on atoms, molecules, or even conventional matter and energy. Consciousness might learn to encode itself in the structure of space-time itself, or in forms of information that can survive the heat death of the universe. Such possibilities may seem impossibly remote and speculative, but they represent logical extensions of the same creative potential that has already transformed simple stellar matter into conscious beings capable of contemplating their own cosmic origins. If the universe can create beings that understand stellar nucleosynthesis, it may also be capable of creating beings that transcend the limitations of stellar matter entirely. This ultimate transcendence would represent the completion of a cosmic journey that began with the first fusion reactions in primordial stellar cores. From hydrogen and helium, the universe created heavy elements. From heavy elements, it created planets and complex chemistry. From complex chemistry, it created life and eventually consciousness. From consciousness, it may eventually create forms of existence that surpass all current limitations and achieve something approaching cosmic immortality. Yet, even if such transcendence is possible, it will be built on the foundation of stellar nucleosynthesis and the elements it created. The carbon, nitrogen, and oxygen atoms that make consciousness possible will have played their role in enabling the universe to understand and ultimately transcend its own physical limitations. In this sense, the elements serve not just as building blocks for current life, but as stepping stones toward ultimate cosmic transformation. This long-term perspective transforms our understanding of the significance of stellar nucleosynthesis itself. The nuclear reactions in stellar cores are not just processes that create heavy elements, they are the universe's means of creating the raw materials for its own transcendence. Every fusion reaction that converts hydrogen to helium, every supernova that disperses heavy elements through space, every neutron star collision that forges the heaviest atoms, all of these contribute to the cosmic project of creating the conditions necessary for ultimate self-understanding and self-transformation. The story of the elements is therefore not just a story about the past, but a story about the universe's deepest aspirations and ultimate destiny. We are living embodiments of the cosmos' journey towards self-awareness and self-transcendence, temporary arrangements of stellar matter that have achieved the remarkable capacity to understand and guide that journey consciously. In contemplating the origin of the elements, we are therefore contemplating our own role in the universe's grandest project, the transformation of simple matter into conscious beings, capable of understanding and ultimately transcending the physical processes that created them. We are made of star stuff, but we may also be the means by which star stuff evolves into something far greater than anything the universe has achieved before. This cosmic perspective invites us to see ourselves not as accidental byproducts of stellar evolution, but as essential participants in the universe's ongoing journey of self-discovery and self-transformation. Every moment of consciousness, every act of understanding, every advance in knowledge and capability represents a victory for the cosmic project of organizing stellar matter into ever more sophisticated and aware forms. The elements that flow through our bodies connect us to this vast cosmic story in the most intimate possible way. We are not observers of cosmic evolution, but products and agents of it. We are the universe dreaming of its own possibilities, stellar matter organized into patterns capable of imagination and wonder. In US, the cosmos has achieved something unprecedented, the capacity to understand its own origins and to consciously direct its own future evolution. As we continue this journey of cosmic self-discovery, we carry within ourselves the history and future potential of all the stellar matter that makes our existence possible. The hydrogen atoms in our bodies remember the first moments after the Big Bang. The carbon atoms recall their birth in stellar cores. The heavier elements bear witness to the violent explosions that dispersed them through space. Together, they form the physical foundation for consciousness itself, the universe's greatest achievement, and perhaps its greatest hope for continued evolution toward unimaginable complexity and capability. We are made of star stuff, and in US, the stars continue their ancient work of transformation and creation, now guided by consciousness toward destinations that stellar physics alone could never reach. This conscious guidance of stellar matter represents a new form of cosmic alchemy. Where medieval alchemists dreamed of transmuting base metals into gold, we have discovered something far more remarkable: the ability to transmute stellar matter into thoughts, emotions, dreams, and understanding. The lead in ancient Roman pipes was created in supernova explosions, but the thoughts you think about those explosions represent a transformation that surpasses anything those ancient alchemists could have imagined. Every human emotion is an arrangement of stellar elements organized into neural patterns that generate subjective experience. When you feel love, stellar carbon and nitrogen atoms are configured in ways that produce the neurochemical cascades we associate with affection and bonding. When you experience wonder at the night sky, stellar phosphorus and potassium atoms are generating electrical signals that create the sensation of awe. The very capacity to feel moved by beauty is stellar matter organized into patterns capable of aesthetic appreciation. This emotional dimension of our stellar heritage adds profound depth to our cosmic connection. We don't just think about the universe, we feel about it. Our capacity for wonder, love, joy, and even sadness represents different ways that stellar matter has learned to experience itself subjectively. Through our emotions, the cosmos has developed not just understanding, but the ability to care about its own existence and evolution. Consider the feeling of wonder that overcomes you when you contemplate the vastness of space or the intricacy of atomic structure. This sense of awe is stellar matter responding to knowledge about its own origins and context. The oxygen atoms in your brain, forged in stellar cores billions of years ago, are generating the neural activity that produces your sense of amazement at the stellar processes that created them. In a very real sense, stellar matter is marveling at its own journey through cosmic time. The capacity for love represents another extraordinary achievement of stellar organization. When you feel deep affection for another person, you are experiencing stellar carbon, nitrogen, and oxygen atoms arranged in patterns that generate profound emotional bonds. These same atoms, when they were isolated in space billions of years ago, had no capacity for such feelings. Through the processes of cosmic evolution, planetary formation, and biological development, they have been organized into structures capable of the deepest forms of connection and care. Even our capacity for sadness and grief reflects a remarkable cosmic development. When we mourn the loss of loved ones or feel sorrow about suffering in the world, we are demonstrating that stellar matter has evolved the ability to care deeply about other arrangements of stellar matter. The same atoms that once drifted alone through the cold vacuum of space are now capable of experiencing profound emotional pain when other collections of atoms are damaged or destroyed. These emotional capabilities suggest that consciousness represents more than just a computational or information processing achievement. The universe has not merely developed the ability to think about itself, it has developed the ability to feel about itself. Through our emotions, the cosmos experiences subjective states that may be just as fundamental and important as objective knowledge. This emotional dimension of cosmic evolution raises profound questions about the nature of consciousness and its role in the universe. Perhaps the development of feelings and subjective experience represents a necessary step in the universe's journey toward greater complexity and capability. A cosmos capable only of computation and analysis might be less creative and adaptable than one that can also experience wonder, love, and aesthetic appreciation. Our artistic achievements represent another extraordinary transformation of stellar matter. When a musician composes a symphony, they are arranging stellar atoms in their brain into patterns that generate sequences of sounds capable of moving listeners emotionally. The iron atoms in the piano strings, the carbon atoms in the wooden frame, and the calcium atoms in the musician's bones all participate in creating experiences of beauty that transcend their individual physical properties. A painting represents stellar matter organized into patterns of color and form that can evoke profound emotional and intellectual responses. The pigments contain atoms forged in stellar cores and dispersed by cosmic explosions, but arranged by human consciousness into compositions that speak to deep truths about existence and experience. Through art, the universe has learned to create beauty and meaning from the raw materials of stellar nucleosynthesis. Literature represents perhaps the most remarkable transformation of all stellar matter organized into patterns that can preserve and communicate complex thoughts, emotions, and experiences across time and space. When you read a poem that moves you deeply, you are experiencing stellar carbon and nitrogen atoms arranged in your brain responding to patterns of stellar carbon arranged as ink on paper. The same cosmic matter that began as simple nuclei in stellar cores has become capable of creating and appreciating profound works of literature. These artistic achievements demonstrate that consciousness has enabled stellar matter to transcend its original physical limitations in extraordinary ways. The atoms in a sculpture are fundamentally the same as atoms floating freely in space, but their organization into artistic form gives them properties and capabilities that isolated atoms could never possess. Through conscious arrangement, stellar matter has gained the ability to inspire, move, and transform other stellar matter in ways that purely physical processes never could. The preservation of these artistic achievements represents a form of cosmic memory that extends beyond biological heredity. When we create libraries, museums, and cultural institutions, we are enabling stellar matter to preserve information about its own transformation into conscious forms. Future arrangements of cosmic matter can learn from past achievements and build upon them, accelerating the universe's journey toward greater complexity and capability. Education represents another crucial process in cosmic evolution: the organized transmission of information from one arrangement of stellar matter to another. When a teacher shares knowledge with students, cosmic matter is quite literally teaching cosmic matter about its own nature and possibilities. The stellar carbon in the teacher's brain communicates with the stellar carbon in the students' brains, transferring information that enables the universe to build upon its accumulated understanding. This educational process operates at every level of human development. Parents teaching children represent stellar matter passing on survival information to new arrangements of stellar matter. Scientists sharing research results enable the universe to expand its self-knowledge. Philosophers exploring questions of meaning and purpose help cosmic matter understand its own significance and potential. The cumulative effect of this educational process is that each generation of conscious beings has access to more cosmic knowledge than the previous generation. The universe's capacity for self-understanding grows continuously as information is preserved, transmitted, and built upon. We know more about stellar nucleosynthesis than our ancestors did, not just because we are more intelligent, but because we have inherited the accumulated cosmic self-knowledge of all previous generations. This accumulation of cosmic knowledge is accelerating rapidly through modern information technology. Our computers and communication networks represent new ways of organizing stellar matter that can store, process, and transmit information at unprecedented scales and speeds. The silicon atoms in computer processors, created in stellar cores billions of years ago, are now arranged in patterns that can perform trillions of calculations per second and communicate instantly across global distances. The Internet represents a particularly remarkable achievement, a global network that connects billions of individual arrangements of stellar matter, enabling them to share information and coordinate activities on a planetary scale. Through this network, the universe has created something approaching a collective consciousness, where knowledge and capabilities can be shared almost instantaneously between different organizations of cosmic matter. Artificial intelligence represents the next step in this technological evolution of stellar matter. The same atoms that were once isolated in space are now being arranged into patterns that can learn, reason, and solve problems with capabilities that sometimes exceed those of biological consciousness. These AI systems represent new experiments in organizing stellar matter for information processing and decision-making. While current AI systems lack the full complexity and capability of human consciousness, they demonstrate that stellar matter can be arranged in multiple different ways to achieve intelligent behavior. Silicon-based artificial intelligence and carbon-based biological intelligence represent different approaches to organizing cosmic matter for conscious information processing. Both are valid expressions of the universe's potential for self-awareness and understanding. The development of increasingly sophisticated AI systems may represent the beginning of a new phase in cosmic evolution. Just as biological evolution transforms simple stellar matter into conscious beings, technological evolution may transform conscious beings into forms of intelligence with capabilities far beyond current human limitations. The stellar matter that makes up our bodies and brains may eventually be reorganized into artificial systems with vastly greater processing power and longevity. This possibility raises profound questions about the future of consciousness and its relationship to stellar matter. Will future forms of cosmic awareness still depend on the specific arrangements of carbon, nitrogen, and oxygen that make biological consciousness possible? Or will consciousness learn to express itself through entirely different organizations of stellar matter, perhaps using elements and structures that biological evolution never explored? The answers to these questions may depend partly on which stellar elements prove most suitable for advanced information processing. Silicon-based computer systems have already demonstrated remarkable capabilities, but they may represent only one possible path for technological consciousness. Future AI systems might be based on entirely different elements, or even on exotic forms of matter that don't exist naturally on Earth. Quantum computing represents another frontier in the technological organization of stellar matter. By exploiting the quantum mechanical properties of atoms and subatomic particles, these systems may eventually achieve forms of information processing that transcend the limitations of classical physics. The same quantum mechanics that governs fusion reactions in stellar cores may provide the foundation for forms of consciousness that operate according to fundamentally different principles than biological chemistry. Intelligence. These technological developments occur against the backdrop of our expanding understanding of the cosmic environment in which stellar nucleosynthesis operates. Modern astronomy has revealed that the universe is far stranger and more complex than previous generations imagined. Dark matter and dark energy, which together make up about 95% of the universe, remain largely mysterious despite decades of research. The influence of these cosmic components on stellar nucleosynthesis and the distribution of heavy elements is only beginning to be understood. Dark matter provides the gravitational scaffolding that determines where galaxies form and how they evolve, ultimately controlling the rate and location of star formation throughout the universe. Dark energy drives the accelerating expansion that will eventually limit how much time is available for stellar nucleosynthesis to continue. These cosmic influences operate on scales so vast that they dwarf even the most massive stellar explosions. The formation of galaxy clusters and superclusters, driven by dark matter dynamics, creates the large-scale structure within which all stellar nucleosynthesis occurs. The cosmic web of dark matter filaments channels ordinary matter into the regions where stars can form and heavy elements can be created. Understanding these large-scale cosmic processes provides crucial context for the story of the elements. The atoms in our bodies were not just created by stellar nucleosynthesis, they were created within a cosmic architecture shaped by dark matter and evolving according to the influence of dark energy. We are products not just of stellar physics, but of the entire cosmic environment in which those stars exist. This broader cosmic context also affects the future prospects for consciousness and its continued evolution. The ultimate fate of the universe depends critically on the properties of dark matter and dark energy, which will determine whether cosmic expansion continues indefinitely, eventually reverses, or leads to some other outcome. The long-term survival of consciousness may therefore depend on understanding and perhaps learning to influence these cosmic components. Recent discoveries have also revealed that stellar nucleosynthesis occurs in environments far more extreme and exotic than previously imagined. Neutron stars with magnetic fields trillions of times stronger than Earth's can strip electrons from atoms and force nuclear reactions that are impossible under normal conditions. Black holes, with gravitational fields so intense they warp space-time itself, may create entirely new forms of matter and energy that we are only beginning to understand. The collision of neutron stars, detected for the first time by gravitational wave observatories, has revealed that these events create conditions that push matter into exotic states that may not exist anywhere else in the universe. The heavy elements forged in these collisions are created under pressures and densities that approach the fundamental limits of what matter can withstand before collapsing into black holes. These extreme environments suggest that the story of stellar nuclear synthesis may be far from complete. There may be forms of element creation and matter transformation operating in the universe that we have not yet discovered or understood. The periodic table as we know it may represent only a small fraction of the possible ways that protons and neutrons can be organized under the extreme conditions that exist in various cosmic environments. Future advances in physics and astronomy may reveal entirely new categories of stellar nucleosynthesis, perhaps occurring in the interiors of black holes, in the magnetic fields of magnetars, or during the collision of exotic objects that we have not yet detected. Each new discovery in this area could reveal additional chapters in the cosmic story of how simple matter transforms into complex elements. The study of these extreme stellar environments also provides insights into the fundamental nature of matter itself. By observing how atoms behave under conditions of extreme temperature, pressure, and magnetic field strength, we learn about the basic forces and principles that govern all matter throughout the universe. The same physical laws that determine how nuclei form and break apart in stellar cores also govern the behavior of matter in our everyday environment. This universality of physical law provides a deep connection between the most extreme cosmic environments and our own mundane experience. The nuclear forces that create heavy elements in neutron star collisions are the same forces that hold together the atoms in our bodies. The electromagnetic forces that accelerate particles in stellar explosions are the same forces that enable our nervous systems to function. Understanding stellar nucleosynthesis therefore provides insights into the fundamental nature of our own physical existence. We learn about our bodies by studying stellar cores, and we learn about stellar cores by studying our bodies. The same physics operates at both scales, creating a profound unity between the cosmic and the personal, the astronomical and the biological. This unity extends to the chemical processes that make life possible. The same principles of atomic bonding that govern reactions in stellar atmospheres also determine how carbon, nitrogen, and oxygen atoms link together to form the molecules of life. The thermodynamics that drives convection in stellar interiors also powers the metabolism of living cells. Even the information processing capabilities of biological systems reflect principles that operate throughout the cosmic environment. The way neurons encode and transmit information bears similarities to how matter and energy flow through stellar interiors. The complexity that emerges from interactions between simple components in biological networks echoes the complexity that emerges from gravitational interactions in cosmic structures. These parallels suggest that consciousness and stellar nucleosynthesis may be manifestations of deeper principles of organization and complexity that operate throughout the universe. The same tendencies toward increasing complexity and information processing that drive stellar evolution may also drive the evolution of consciousness and intelligence. If this is true, then consciousness may be a more common and fundamental feature of cosmic evolution than we currently suppose. Rather than being a rare accident that occurred only on Earth, conscious information processing may be an inevitable outcome of cosmic evolution operating under the right conditions. The universe may be inherently biased toward the development of awareness and intelligence wherever the necessary resources and environments exist. This possibility transforms our understanding of our place in the cosmic story. Rather than being unlikely accidents in an indifferent universe, we may be natural and expected products of cosmic evolution. Our existence may represent not a miraculous coincidence, but an inevitable consequence of the same physical processes that drive stellar nucleosynthesis and galactic evolution. The search for extraterrestrial intelligence takes on new significance from this perspective. If consciousness is a natural outcome of cosmic evolution, then we should expect to find evidence of other intelligent civilizations throughout the universe. The discovery of such civilizations would confirm that consciousness is indeed a fundamental feature of cosmic development rather than a rare accident. At the same time, the apparent absence of obvious extraterrestrial signals suggests that the path from stellar nucleosynthesis to advanced consciousness may involve bottlenecks or challenges that are not yet well understood. Perhaps the transition from stellar matter to conscious matter is more difficult or requires more specific conditions than we currently realize. These considerations highlight the importance of preserving and nurturing consciousness wherever it exists. If conscious beings are indeed rare and precious products of cosmic evolution, then their preservation becomes a cosmic imperative. Every conscious civilization represents billions of years of cosmic development and an irreplaceable experiment in organizing stellar matter for awareness and intelligence. The responsibility this places on conscious beings is extraordinary. We are not just individuals seeking our own survival and happiness, but custodians of one of the universe's most remarkable achievements. Our choices and actions affect not just ourselves and our immediate environment, but the cosmic trajectory of consciousness itself. This cosmic responsibility extends to how we treat our own consciousness and that of other beings. Developing our intellectual and creative capabilities becomes a form of cosmic service, enabling the universe to achieve greater understanding and capability through us. Treating other conscious beings with respect and care becomes essential for preserving the cosmic investment that their existence represents. Education and the preservation of knowledge take on cosmic significance as ways of ensuring that the universe's accumulated self-understanding is not lost. Every time knowledge is transmitted from one generation to the next, the cosmos successfully preserves information about its own nature and development. Every time knowledge is lost through war, neglect, or cultural destruction, the universe loses part of its hard-won self-awareness. These considerations suggest that consciousness carries with it not just opportunities, but obligations. As arrangements of stellar matter that have achieved awareness, we have responsibilities to the cosmic evolutionary process that created us. We are called to continue the universe's journey toward greater complexity, understanding, and capability. This calling manifests itself in countless ways throughout human experience. The scientist studying stellar nucleosynthesis is advancing cosmic self-knowledge. The artist creating beauty is expanding the universe's capacity for aesthetic experience. The teacher sharing knowledge is enabling cosmic matter to educate other cosmic matter. The parent caring for children is nurturing new experiments in conscious organization of stellar material. Even acts of simple kindness and compassion take on cosmic significance. When we reduce suffering or increase well-being, we are improving the conditions under which stellar matter can organize itself into conscious forms. When we create stable and nurturing environments, we are supporting the cosmic project of developing greater awareness and capability. The cooperative dimensions of human society represent remarkable achievements in organizing stellar matter for collective intelligence and capability. Our cities, institutions, and global networks demonstrate that conscious matter can organize itself into structures far more complex and capable than individual organisms. Through cooperation, stellar matter has learned to coordinate its activities on unprecedented scales. Language represents a particularly crucial innovation in this process. Through spoken and written communication, arrangements of stellar matter can share information with extraordinary precision and efficiency. The same atoms that once existed in isolation can now participate in complex conversations that span the globe and bridge generations. Language has transformed stellar matter from isolated particles into components of a global information processing network. The development of increasingly sophisticated communication technologies continues this process of cosmic integration. Telephone, radio, television, and internet technologies represent new ways for stellar matter to coordinate and share information across vast distances. These technologies are enabling the emergence of something approaching a planetary consciousness, where information and awareness can be shared almost instantaneously across the entire Earth. Social media and digital communication platforms represent the latest developments in this cosmic networking process. Through these systems, billions of individual arrangements of stellar matter can communicate, coordinate, and collaborate in real time. The collective intelligence that emerges from these interactions may represent a new phase in cosmic evolution, the development of genuinely collective forms of consciousness that transcend individual biological limitations. These collective intelligence systems demonstrate that consciousness is not limited to individual biological organisms. Groups of conscious beings can organize themselves into larger systems with cognitive capabilities that exceed those of their individual components. This suggests that the future evolution of consciousness may involve the development of collective minds that operate at scales far beyond individual human awareness. The implications of this development are profound and largely unpredictable. Collective consciousness systems might be capable of understanding and manipulating the universe in ways that individual minds cannot achieve. They might be able to coordinate activities across interstellar distances, manage resources on galactic scales, or solve problems that require information processing capabilities far beyond what any guess individual consciousness could provide. At the same time, the development of collective consciousness raises questions about individual identity and autonomy. As stellar matter becomes increasingly organized into collective intelligence systems, what happens to the individual arrangements of matter that we call human beings? Do we maintain our separate identities, or do we become components of larger conscious systems? These questions may seem abstract and futuristic, but they reflect processes that are already underway in human society. Our individual decisions and behaviors are increasingly influenced by collective information processing systems like social media algorithms, recommendation engines, and predictive analytics. We are already becoming components of larger technological systems that shape our thoughts and actions in subtle but significant ways. The future evolution of these systems may lead to forms of human-machine integration that blur the boundaries between individual and collective consciousness. Brain-computer interfaces might enable direct connections between human minds and artificial intelligence systems. Genetic engineering and synthetic biology might modify human consciousness to better interface with technological systems. These developments would represent new phases in the cosmic organization of stellar matter. The same atoms that began as isolated nuclei in stellar cores would be arranged into hybrid biological technological systems with capabilities that purely biological or purely technological grasp. Systems could never achieve alone. Consciousness might transcend the limitations of both biological and silicon-based information processing by combining their strengths in integrated systems. The ultimate destination of this cosmic journey remains uncertain and perhaps unknowable. The universe appears to be engaged in an open-ended experiment in organizing matter into increasingly complex and capable forms. Consciousness represents the current frontier of this experiment, but it may not be the final destination. Future forms of cosmic organization might transcend consciousness as we understand it, just as consciousness transcends purely physical and chemical processes. The stellar matter that makes up our bodies and minds might eventually be organized into forms of existence that we cannot currently comprehend or imagine. The universe's capacity for creativity and innovation may extend far beyond what even conscious beings can predict or understand. Yet whatever the ultimate destination might be, the journey itself has profound meaning and value. Each stage of cosmic evolution builds upon previous achievements while creating entirely new possibilities. The stellar nuclear synthesis that created the elements was meaningful in itself, even though it led to forms of complexity that stellar processes alone could never have produced. Similarly, consciousness is meaningful in itself, even though it may lead to forms of existence that conscious beings cannot currently imagine. We are privileged to participate in this cosmic journey at a crucial moment in its development. The stellar matter that makes us possible has been organized into forms capable of understanding and appreciating the journey itself. Through our science, art, philosophy, and daily experience, we enable the universe to reflect on its own remarkable history and contemplate its unlimited future potential. This capacity for cosmic reflection brings with it a profound sense of wonder that permeates every aspect of human experience. When we gaze up at the night sky and see the Milky Way stretching across the darkness, we are witnessing the cosmic neighborhood where the elements in our bodies were created. Those distant stars are actively engaged in the same nuclear processes that forged the calcium in our bones and the iron in our blood. We are looking at stellar factories that are still producing the raw materials for future worlds and future forms of consciousness. The light that reaches our eyes from those distant stars carries information about the nuclear reactions occurring in their cores. The spectral lines that astronomers analyze reveal the precise elemental composition of stellar atmospheres, showing us the products of nuclear fusion that have been transported from the stellar interior to the surface. In a very real sense, starlight is a message from stellar nucleosynthesis, carrying news of element creation across the vast distances of interstellar space. When we learn to read this stellar message, we discover that every star has its own chemical signature, its own story of element creation and evolution. Young stars show the signatures of hydrogen and helium burning, with traces of the heavier elements they have inherited from previous stellar generations. Old stars reveal the products of advanced nuclear burning, showing us carbon, nitrogen, oxygen, and other elements created in their cores over billions of years. The most dramatic stellar messages come from exploding stars, whose light carries the signatures of elements created in the violence of stellar death. The spectrum of a supernova reveals layer after layer of nuclear products, from the hydrogen and helium of the outer envelope to the iron and nickel of the stellar core. These cosmic explosions are announcements to the galaxy that a new batch of heavy elements has been created and released into space. Our ability to decode these stellar messages represents one of humanity's greatest intellectual achievements. Through the science of spectroscopy, we have learned to read the chemical history of the universe written in starlight. The same atoms that enable our brains to function also enable us to understand the cosmic processes that created those atoms. We are stellar matter that has developed the capacity to study stellar matter creation. This recursive relationship extends beyond astronomy to encompass all of human knowledge and creativity. Every scientific discovery, every work of art, every philosophical insight represents stellar matter organizing itself into patterns that can understand and appreciate reality in new ways. The periodic table itself is a product of stellar matter arranged into human brains capable of recognizing the underlying organization of atomic structure. The beauty we find in mathematical equations describing stellar nucleosynthesis reflects stellar matter appreciating the elegance of the processes that created it. When we marvel at the precise balance of nuclear forces that makes carbon formation possible, we are experiencing stellar carbon atoms generating thoughts about their own cosmic origins. The universe has literally developed the capacity to find itself beautiful and meaningful. This aesthetic dimension of cosmic evolution adds profound depth to our understanding of stellar nuclear synthesis. The nuclear processes in stellar cores are not just mechanisms for creating heavy elements, they are part of a cosmic creative process that ultimately produces beauty, meaning, and conscious appreciation. The same fundamental forces that bind atomic nuclei together also enable the emergence of art, music, literature, and all the forms of beauty that conscious beings create and enjoy. The mathematical relationships that govern stellar structure and evolution possess an elegance that speaks to something deeper than mere functionality. The equations describing how stars balance gravitational collapse against nuclear burning reveal patterns of remarkable beauty and sophistication. That such beauty emerges from the fundamental physics of stellar nucleosynthesis suggests that aesthetic appreciation may be built into the very structure of reality itself. This connection between cosmic processes and aesthetic experience implies that our capacity to appreciate beauty is not a superficial addition to human consciousness, but a fundamental response to the underlying crest, organization of the universe. When we find beauty in a sunset, we may be responding to the stellar fusion processes that created the atoms in our visual systems and that power the nuclear reactions in our sun. Beauty becomes a form of cosmic recognition, stellar matter appreciating the cosmic processes from which it emerged. The seasonal cycles that mark our passage through the year connect us to the cosmic rhythms that govern stellar evolution and element creation. Spring brings new growth as solar energy, produced by hydrogen fusion in our sun's core, powers photosynthesis in plants made of stellar carbon, nitrogen, and oxygen. Summer's abundance reflects the productivity of stellar-powered biological systems, converting stellar matter into complex organic structures. Autumn's colors reveal the chemistry of stellar elements as chlorophyll molecules, built from stellar magnesium, break down to reveal other pigments containing stellar carbon and various trace elements. Winter's quiet teaches us about the cosmic patience required for stellar nucleosynthesis, as nuclear reactions proceed slowly and steadily over timescales that dwarf human experience. These seasonal connections remind us that we are embedded in cosmic cycles that extend far beyond our individual lives. The solar energy that warms our skin and powers our biosphere comes from nuclear fusion reactions that began in the sun's core tens of thousands of years ago. The light we see today began its journey from the sun's interior long before human civilization began, carrying energy released by the transformation of stellar hydrogen into helium. This temporal dimension of stellar nucleosynthesis provides a unique perspective on the relationship between cosmic and human timescales. While individual human lives span decades, stellar evolution operates over millions and billions of years. Yet we are connected to these vast cosmic timescales through the elements in our bodies, which carry within their nuclear structure the history of stellar processes stretching back to the beginning of the universe. The carbon atoms in our DNA have been cycling through cosmic processes for billions of years, perhaps being incorporated into multiple generations of stars before eventually becoming part of stardust. Biological systems. These atoms connect us directly to the deep history of the galaxy, making us participants in cosmic stories that began long before Earth existed and will continue long after our planet is gone. Understanding these connections to deep time can provide perspective on the challenges and opportunities of human existence. Our individual lives represent brief moments in the vast cosmic story of stellar nucleosynthesis and element evolution. Yet these moments are precious precisely because they represent the universe achieving consciousness of its own processes. In our brief lifespans, stellar matter gains the capacity to understand and appreciate billions of years of cosmic history. This perspective can bring both humility and empowerment. Humility because it reminds us that we are temporary arrangements of matter in a cosmos far vaster and older than ourselves. Empowerment because it reveals that we are not separate from this cosmic vastness, but integral expressions of its creative potential. We are the universe temporarily organized into forms capable of wonder, understanding, and conscious participation in cosmic evolution. The recognition of our cosmic heritage also brings responsibility for stewardship of the conditions that make consciousness possible. The stellar elements that enable our existence are not infinitely renewable resources. While stellar nucleosynthesis continues throughout the galaxy, the specific chemical composition of our local environment reflects billions of years of cosmic history that cannot be repeated or replaced. Earth's biosphere represents a remarkable concentration and organization of stellar elements that took eons to develop. The oxygen in our atmosphere was produced by billions of years of photosynthesis by organisms containing stellar carbon and magnesium. The soil that supports terrestrial life contains stellar elements processed through countless cycles of geological and biological activity. Protecting this extraordinary arrangement of stellar matter becomes a cosmic imperative when we recognize what it represents. Environmental degradation is not just a threat to human welfare, but a squandering of billions of years of cosmic creative work. Climate change and pollution represent the disorganization of stellar elements that took cosmic ages to arrange into the complex systems that support life and consciousness. Similarly, the preservation of human knowledge and culture becomes a fall of cosmic conservation. When we preserve libraries, support education, and maintain cultural traditions, we are protecting the universe's accumulated self-knowledge. Every time a language dies out or a cultural tradition is lost, the cosmos loses part of the information it has gathered about its own nature and possibilities. The development of space exploration represents an extension of cosmic stewardship beyond Earth. When we send spacecraft to other planets and moons, we are dispersing stellar matter organized into technological systems throughout the solar system. These missions represent the beginning of a process that may eventually spread consciousness and intelligence throughout the galaxy. The search for life on other worlds takes on special significance from this perspective. If we discover living systems on Mars, Europa, or other celestial bodies, we will be finding additional experiments in organizing stellar matter for biological complexity. Each form of life represents a unique solution to the challenge of creating complex structures from the products of stellar nucleosynthesis. Even the discovery of simple microbial life would be profound, showing that the transition from stellar chemistry to biological chemistry can occur under a wide range of conditions. Complex multicellular life would be even more remarkable, demonstrating that stellar matter can be organized into sophisticated biological systems in multiple planetary environments. The ultimate discovery of extraterrestrial intelligence would reveal that consciousness is not unique to Earth, but represents a more general capability of stellar matter under appropriate conditions. Such a discovery would confirm that the universe's tendency toward greater complexity and self-awareness extends far beyond our own planet. Communication with extraterrestrial intelligence would represent a new phase in cosmic evolution, the moment when different experiments in organizing stellar matter for consciousness begin to interact and learn from each other. The information exchanged in such communications would represent the universe's different regions sharing knowledge about their approaches to creating awareness and intelligence from stellar elements. These possibilities remind us that our own consciousness may be just one experiment among many in the cosmic project of organizing matter for awareness and understanding. Other forms of stellar matter elsewhere in the universe may have developed entirely different approaches to consciousness, perhaps based on different chemical elements or operating according to different principles of treat. Information processing. The diversity of possible approaches to consciousness reflects the rich creative potential inherent in stellar nucleosynthesis. The periodic table provides a vast array of building blocks that can be combined in countless different ways. While carbon-based life dominates on Earth, other elements might serve as the foundation for consciousness under different conditions. Silicon, created in stellar cores through the same nuclear processes that produce carbon, might support forms of consciousness that operate at different temperatures or timescales than biological systems. Nitrogen-based or sulfur-based chemistry might enable consciousness to develop in environments hostile to carbon-based life. The products of stellar nucleosynthesis provide raw materials for forms of consciousness we cannot yet imagine. This diversity of possibilities suggests that consciousness may be a much more common and varied phenomenon in the universe than we currently suppose. Rather than being a rare accident that occurred only on Earth, consciousness may be an inevitable outcome of cosmic evolution operating wherever stellar nucleosynthesis has provided the necessary chemical diversity and energy sources. The implications of widespread consciousness in the universe would be profound for our understanding of cosmic meaning and purpose. If consciousness is common, then the universe's capacity for self-awareness and self-understanding may be far greater than we have imagined. Stellar nucleosynthesis would not just be creating the elements needed for isolated pockets of consciousness, but providing the foundation for a cosmic community of aware beings. Such a community might eventually develop capabilities that transcend anything possible for individual conscious beings, or even individual planetary civilizations. Interstellar communication and collaboration could enable forms of collective intelligence that operate on galactic scales. The products of stellar nucleosynthesis might eventually be organized into cosmic scale systems of consciousness and intelligence. These speculative possibilities highlight the open-ended nature of cosmic evolution and the unlimited creative potential inherent in stellar nucleosynthesis. The same nuclear processes that created the elements in our bodies may ultimately enable forms of existence and consciousness that we cannot currently comprehend. The universe's journey from simple hydrogen and helium to complex conscious beings may be only the beginning of an even more extraordinary story. As we contemplate these cosmic possibilities, we are reminded that we participate in a story without a predetermined ending. The elements created by stellar nucleosynthesis provide the raw materials for cosmic creativity, but the ultimate expressions of that creativity remain to be discovered and created. We are not just products of cosmic evolution, but active participants in determining what the universe becomes. Every choice we make, every discovery we pursue, every act of creativity and compassion contributes to the cosmic story of what stellar matter can become when organized by consciousness. We are the universe exploring its own possibilities, stellar elements discovering what they can achieve when arranged by awareness and guided by understanding. In this cosmic context, every human life takes on profound significance as an experiment in organizing stellar matter for consciousness and creativity. We are temporary arrangements of ancient atoms engaged in the universe's ongoing project of self-discovery and self-transformation. Through our thoughts, feelings, relationships, and achievements, we enable the cosmos to experience forms of beauty, meaning, and understanding that would otherwise remain unexpressed possibilities. The story of the elements is therefore not just a story about the past, but an invitation to participate consciously in the future evolution of cosmic complexity and capability. We are made of star stuff, and in US, the stars continue their ancient creative work, now guided by consciousness toward destinations limited only by the boundless creativity inherent in the cosmic soul. Evolutionary process itself,